So we used a YouTube poll on the channel to select the next videos, and the first two winners were black hole powered spaceships and faster than light travel. There's a lot of overlap in some of those concepts, and when I realized I was 20 minutes into the video for the first one, before I even mentioned how those spaceships might work, I decided I'd just go ahead and make both of them and this video all part of a set. Today I'm explaining the concept of micro black holes, how they differ from regular black holes, and how we might go about making these things. To properly discuss that, we need to talk about Hawking radiation. And to do that, we need to talk about virtual particles. But when we're talking about black holes, we first need to clear away a lot of the misconceptions people tend to get about black holes. Which is to say, they're not black and they're not holes. That term, black hole, didn't even come into use till the late 1960s. On the other hand, the notion has been around since well before Einstein discussed the concept of general relativity. They first got discussed way back when the American Revolution was going on. A lot of the common features of black holes people reference either are limited to naturally occurring ones made of dead stars, or actually describes the tiny condensed matter, probably a point-like object of infinite density, inside the black hole, called a singularity. But a black hole itself is simply any region of space where the escape velocity exceeds the speed of light, and we often call that the event horizon because it's the place where you can't see events occurring on the other side. Nothing that happens on that other side, no event, can be witnessed externally because the light never reaches you from it. This does not mean all black holes are dense. The monstrously huge ones at the center of many galaxies have an average density less than white dwarfs or neutron stars, for instance, and one formed from an entire galaxy's mass would be nearly a light year across, and for all that contained a trillion stars worth of matter, it would have an average density on par with the air you and I are breathing. Stellar mass black holes are very dense, since they are squeezing the mass of a whole star into an area a few miles across. Smaller black holes are a lot denser than even that. An Earth-mass black hole would be about the size of a marble and fit comfortably in your hand, at least until it tore you apart and sucked you in. But a lot of the black holes we'll be interested in the next video, to be used as power sources, are way smaller than even that, and they actually wouldn't suck you in. They simply lack enough mass to yank on you. They're also so small they have problems absorbing matter. That's made worse by the Hawking radiation, which we'll get into later. So if I collapsed an entire small mountain, a billion or so tons of matter, into a black hole, that black hole would be about the size of a proton. If we stuck it in a room on a pedestal, you'd be quite safe standing on the other side of the room from it. Though when you got to about an arm's length, it would be yanking on you as hard as the Earth does. Almost all of the micro black holes we'll be interested in this and the follow-up videos will be even less massive than that, and in most cases, if it weren't for the Hawking radiation they emit, they wouldn't hurt you if you walked right past them. That Hawking radiation does matter though, because we'll see in a little bit, while your average dead star black hole doesn't even emit enough energy via Hawking radiation over 1 billion years to power a light bulb for a millisecond, smaller ones release a lot of energy, and the smaller they are, the more they produce. This billion-ton one we just mentioned releases an amount of power comparable to a nuclear power plant or a major hydroelectric dam. So while you could safely stand across the room from it without being dragged in, the power coming off it would burn you to a crisp, since it would be about 1,000 times more potent than noontime sunlight, even at the other side of a fairly large room. Before we get into Hawking radiation and virtual particles, we have to talk about gravity gradients and tidal forces. You've probably heard that you fall towards a black hole and will get torn to shreds. The official scientific name of this is spaghettification, because you get stretched out thin, then ripped apart. Personally, I don't like this being mentioned in regard to black holes because it gives some weird notions and feeds into misconceptions that black holes are incredibly dangerous compared to normal stars. A stellar mass black hole wouldn't shred you till you got way closer to it than the original parent star would have torched you into atomic dust at. In fact, you need to be a lot closer than a planet's distance, and if you fell toward the Earth, you get burned up and hit the ground way before you get to the tidal tearing distances of most stellar mass black holes. Now they all have a distance that would shred you, assuming they have a singularity or a near singularity in their middle anyway. But for galactic central black holes, it is way after you've already fallen into the event horizon, and for micro black holes, it's at distances less than most atoms are wide. The cause for this is the same in all cases. Gravity is an inverse square force. Get twice as far away, and gravity has 1/4 of its strength. Get half as close, and it's 4 times more powerful. Any object is going to experience slightly less gravity on its bottom than its top. Gravity is just a bit weaker up there. On planets, that's as far as it goes, because the mass is all spread out, so that even if you drill down deep into the Earth, gravity doesn't get stronger. In fact, in the center of Earth, there's no gravity at all, because all the matter is symmetrically spread around you, canceling out, not working together like when you're outside of it. Black holes are all concentrated, so you can get very close, to a distance where your head might be twice as far from the center as your feet, and would experience 1/4 the pull of gravity as your feet. And if you're near a normal black hole, that gravitational difference might be only a fraction of a percent, but it's a fraction of a percent of millions of times more gravity than you experience on Earth, so it stretch you and rip you apart. This tidal force, this gravity gradient, is very important in smaller black holes, because it means that over a very small distance, distances the size of atoms or smaller, that difference in gravity might be truly massive. While in larger black holes, for all that they have a lot of gravity, the difference in it, at only an atom width or further away, aren't that large out above the event horizon. Remember that because we'll come back to it. Smaller black holes can have tidal forces above their event horizons so severe that they could rip an electron off an atom simply because it was slightly closer. So let's talk about virtual particles. At the core of physics, especially in quantum mechanics, there's a bit of a conundrum with how attractive forces work. If you've got two positive charges, like repels like, and we envision this as both spitting out photons that hit each other and shove each other further away, that doesn't work too well with attraction. Normally, if you chuck a baseball at someone, it shoves them further away, it doesn't drag them closer. So in quantum field theory, we fix this with something called a virtual particle. Particles that don't have to follow the normal rules, like having positive mass, positive momentum, positive energy, obeying the speed of light, or even moving forward in time. Now, while these particles are literally pulled from nowhere, the concept isn't. The keystone of quantum mechanics is the uncertainty principle. That holds that when you get down to really small scales, certain complementary variables like position and momentum, or energy and time, can only be simultaneously measured with so much accuracy. Conceptually, it's sort of like fractions of a penny. If something costs 99 cents and there's a 6% sales tax, you pay $1.05, though 106% of 99 is actually 104.94. That 6/100ths of a penny got rounded up. The universe is a bit like that too. It can't keep track of fractions of cents, and the amount it can't keep track of, its fraction of a penny, is Planck's constant. A lot of particles that mediate forces, like the W and Z bosons that regulate the weak nuclear force, are actually way more massive than the particles that emit them. And this force has an incredibly short range because that amount of mass and energy can only exist out of nowhere like that for a very short period of time, so these particles can't travel far before disappearing, giving the weak nuclear force a very short range. For virtual particles, they come into existence, the theory goes, in pairs right out of nothing. We call this the quantum foam these days. If you've ever heard references to vacuum energy or zero-point energy or weirdness with the Casimir effect and wormholes, this is what that originates from. And we've measured the Casimir effect in labs, so again this idea isn't coming out of nowhere, even though it's based on the idea of things popping out of nowhere. So virtual particles appear in pairs out of nowhere. These are opposite particles of each other, akin to antimatter. They pop up right next to each other and almost always nearly instantly recombine and annihilate. Virtual particles don't have to have the same energy or mass as their real-world equivalents, since the uncertainty principle permits them to vary off the expected normal amounts quite a lot. This normal, what particles have when we graph their energy, mass, and momentum in terms of classical mechanics, forms up a hyperboloid that looks a bit like a shell. So we call normal matter as being on shell or on mass shell, and virtual particles can be off mass shell. And conceptually, how far you are off shell is sort of a measure of how unreal a particle is and how short its existence. Though there are ways for virtual particles to become real, and the divide between real and virtual particles can be a bit blurry and arbitrary in some cases. In another way of looking at virtual particles, they don't so much exist in space and time as they occupy the moment between the ticks of the clock or the cracks between the flagstones. I like that analogy personally, since they are basically the mortar holding the bricks of matter together. Non-virtual, real matter that has these properties like negative mass or energy is generally what is being referred to when we talk about exotic matter, which will be a big component of a lot of the various ideas we will talk about in the Faster Than Light video in a couple of episodes. Incidentally, quite a few of the notions kicked around for where all the matter and energy of the Big Bang came from often revolve around virtual particles or parallel concepts from string theory, a sort of notion of the whole universe being a big vacuum fluctuation. There's not much evidence of this, but there's not much evidence of anything else from that event either, and as ex nihilo theories go, those tend to be some of the more interesting ones. But the basic theory dealing with quantum foam holds that virtual particles are constantly popping out in pairs everywhere, pairs that almost immediately negate each other out. Now we get to Hawking radiation, because as I mentioned earlier, on very small black holes, the tidal forces right near the event horizon can be so strong that a pair of particles right next to each other, but with one just a tiny sliver of distance further away, might be ripped apart by the difference in forces. Now normally, just above a black hole event horizon, just like everywhere else, pair production of virtual particles is constantly going on. Sometimes both will escape, sometimes both will fall in, and nothing important has happened. Literally nothing has actually happened. But every so often, one virtual particle will fall into the black hole, and the other one will fly away. Separated by an event horizon, they can't recombine or talk, and the black hole will just lose a little mass or energy. Same difference in this context, as the one virtual particle flies away and becomes real. Normally a photon, a big gamma one, but it can be other particles too. This doesn't happen much. Around the big black holes, this happens almost never, even though there's a lot more real estate right over the event horizon of a bigger black hole, and way more virtual particle pairs being produced. Around the smaller ones though, right over their event horizons, the difference in forces over even subatomic distances can be massive. Massive enough to yank those two particles apart and pull one under the horizon, and to do this quite regularly. This makes the black hole emit energy, which we call Hawking radiation since it was Stephen Hawking who figured this out in 1976. And we call this process black hole evaporation, as it means that unless a black hole is absorbing replacement matter, they will eventually shrink in size and will keep shrinking even faster. So while a stellar mass black hole might let one virtual photon fly free and become real every couple of years, and thus take tens of millions of trillions of trillions of trillions of trillions of trillions of years to evaporate, a smaller one, that billion-ton mountain mass one we looked at earlier, should emit a few hundred megawatts of power constantly for a mere couple trillion years. A fly speck of time to evaporate, just a couple hundred times longer than the universe has already existed. And a few hundred megawatts is a pretty nice power supply, comparable to most nuclear reactors. Very loosely, black hole power output by Hawking radiation scales up with the inverse square of its mass, meaning if the black hole's mass is cut in half, we expect to get 4 times the power. It would also mean it only lived 1/8 the time, since it's losing mass energy 4 times as fast, and only half as much of it exists to burn in the first place. So if you want a black hole power source that would just outlive our sun, it would only mass about 100 million tons, 100 megatons, the mass of a decent-sized hill, and would pump out about 30 billion watts of power continuously for the next 4 billion years. That's a lot of juice, about enough for 10 million people by modern US electrical consumption. And 100 megatons isn't that much mass. I mean, it is a lot. In terms of water, that would be enough to fill a stadium to the brim several dozen times. But the oceans hold over 1 billion megatons of water, and the planet itself masses about 6 quadrillion megatons, so in the grand scope of things, it ain't that much mass. Now, while there is a lot of juice and not that much mass, it's still way too little power for way too much mass to make it a good spaceship. So when we talk about black hole powered spaceships in the next video, we will be looking at ones closer to the 1 megaton range. For mostly stationary things, at least in interstellar terms, like space stations and planets, these hill-mass black holes are where it's at. They can last millions or billions of years and produce more power than an equal mass of solar panels or wind turbines or other things that don't use limited supplies of fuel like petroleum or uranium. And they take up a lot less room than fields of solar panels or wind turbines since they are smaller than a proton. Which also means if you built one on the Earth, it would just fall right down, and then back out the other side of the planet and back up in a 80 minutes. I mean, it's way smaller than an atom, yet it would still be carrying all the inertia of a free-falling asteroid. It won't run into much friction from collision. It would just oscillate back and forth every 80 minutes, scorching a nice line along the way. That's one reason why we don't worry much about accidentally making black holes in the lab. Even if we made one, it would have way less mass than 100 megatons. We'd be talking grain of sand levels of mass, and lifetime's so short we can only talk about them in scientific notation, so it would just flash right out of existence. But even if it didn't, it would just harmlessly oscillate through the planet every 80 minutes, though you often see that listed as 84 minutes. The time it takes for something to fall down and through an object to its other side and back again, if it's not slamming into things, like if you drilled a frictionless vacuum tunnel right through the planet, is based entirely on the density of the planet, not its size. That's the core of the concept called a gravity train. One of the subscribers was asking about it recently, and it was in that Total Recall movie, the remake, not the original, which personally I liked, even if it wasn't as good as the original. Normally we use gravity train concepts for skimming Batchistochrone curves between two cities on the same continent, rather than passing through a planet's molten core. Basically, you'd fall down a frictionless vacuum tunnel between, say, New York and Cleveland, using no power, which is an unrelated but fun concept we might look at down the road. There are some tricks to keep black holes from plummeting, but the easiest would probably be just to make the thing up in geostationary orbit, then beam the power down. I know I generally disdain beaming power, since a power beam able to supply electricity for 10 million people is also known as a death ray, especially considering Hawking radiation is normally hard gamma, but it deserves mention. I will talk about weaponizing micro black holes a bit in the next video, but we'll skip that for now. I get asked fairly frequently to do videos on super weapons, which is an interesting collection of options, but if my supervillain vibe gets any stronger, I'm gonna have to start picking out a location for my lair, so that's on the back burner. Besides, I already did a top 10 video of ways to wipe out a planet's population last year. You get around the gamma radiation by wrapping the black hole in something that was a good absorber and had a high melting temperature, like tungsten, which for a 30 gigawatt hill mass black hole would mean a spherical shell of tungsten a couple hundred feet across that would be glowing red hot. You could then trap that power with solar panels, or just leach the heat off of it classically to boil water and turn turbines, though the latter is a pretty counterintuitive setup in zero gravity. Now, making black holes is also a problem. Not as bad as refueling them so they don't explode, which we'll talk about in the next video, since the ones for spaceships tend to have lifetimes where you'd actually need to worry about them exploding, but it is still quite a technical hurdle. It doesn't appear to be a physics hurdle though. As best as we can tell, there isn't a specific problem making small black holes that violates some known law of physics, though that's always hard to be sure of since we don't know much about black holes definitively yet, and there's still debate about if black holes themselves might violate the laws of physics. For very big ones, it's conceptually easy. Cram a lot of mass together, bingo, black hole. But matter doesn't like to be crammed together, and for smaller ones, you don't even have gravity helping you pack it in tight. So the popular theoretical methods is to blast lasers together, since photons are bosons, and unlike fermions, which pretty much everything you think of as normal matter is, they don't care if you jam them together. Photons are incorporeal, as it were. All bosons are. Any number of them can occupy the exact same place at the same time, though space and time start getting a bit inaccurate as concepts at that scale. You can read up about that under the Pauli exclusion principle if you want more details. So if you fired a bunch of photons, all aimed at the same place to arrive at the same time, and you packed enough energy in that spot to form a black hole, you've got one. Normally you'd do this with gamma radiation, since it has a way smaller wavelength, which is important when you're trying to target a spot smaller than atomic nuclei. Now, doing this would require some amazing precision, and a big initial power supply, though you could draw that out by bouncing stuff around mirrors or similar. You could also control the initial conditions of the black hole if your accuracy is good, giving it the spin or lack of spin you want, as well as an initial velocity of the direction and speed you want. Incidentally, doing it this way means your black hole is not a power source, it's a battery, since you're feeding all that energy into it from a massive solar array. Fortunately, the sun puts out about 1 billion times more power than hits Earth, and if you were using all that power just to manufacture the 100 megaton hill mass black holes we've been discussing, which by good old E equals mc squared have just under 10 to the 28th joules of energy in them, you could manufacture a new one a couple times a minute using the total solar output. And it might be a battery in this context, but since you could control its initial velocity, and they are capable of providing significant thrust by themselves, that's what the whole next video is about, these black hole batteries are very handy things for powering anything decently far from the sun or that's compact. Alternatively, a fusion reactor isn't a battery, which is why I often talk about future power sources and just talk about them. But in the context of batteries, or fuel for ships, they seriously surpass fusion and are potentially way lower maintenance too. I talked about making small fake suns that orbited their planets geocentrically in the ShellWorlds and Discworlds videos, and these are sort of ideal for that task, since you just build one, or a collection of black holes, of the right power output and lifetime, stick a shell around them of something with a high melting point, and dump it into a 24-hour orbit around the fake planet. Real quickly, refueling black holes, small black holes anyway, is harder than making them because dumping matter into an object that is smaller than an atom and spraying out gigawatts of power is sort of like trying to throw a beach ball into the nozzle of a fire hose that's turned on. We'll talk about that more next time, but I think we've reached a good place to end for now. Next time, black hole-powered starships, which is going to be a bit more sci-fi focused, and after that we'll talk about theories for faster light travel and communication, which is also going to be pretty sci-fi oriented, though as always we'll keep it as close to hard science as possible. No poll this time since I already know what the next 2 videos are going to be, but I'm always collecting ideas for new videos, so please leave suggestions down in the comments section along with any questions. If you enjoyed the video, hit the like button and share it, and if you're new to the channel, hit the subscribe button so you can be alerted when new videos come out, and try out some of these other video playlists. As always, thanks for watching, and we'll see you next time.